So relation of functions less than 1, so this would be unit 7 for us. Review preview. So the Cartesian coordinate system. In mathematics, Cartesian means relating to French mathematician Descartes. Okay. Let's go back up here. Okay. So the coordinate system is a label with an x and y axis. So as you can see right here, this is a coordinate system right here. You don't have to call it Cartesian every time, but if you ever hear that, just remember that's just an xy coordinate system. It relates x and y. So it's best used for graphing lines, etc. So let's just kind of go through here. Two axes, x and y. Okay, the point of intersection of two axes is called the origin. That's pretty important labeling. Okay, so if you would like to, that's what that little O right there is for, is the origin. That's like your center point. That's 0, 0. Okay, it's called the origin. Okay, on each axis, a unit length is chosen. Units are marked off from the grid. So what that means is you can have your coordinate grid be whatever scale you want and by whatever units you want. Like let's say you're doing something in meters. You can make it go by every 3 meters if you want it. You can always adjust it however you want. Just be consistent, right? So like, does that make sense? You can scale any way you'd like. Okay. So the first number. Okay, so the first number in your point, and really have to slow me down here a little bit, guys, because I've actually never taught the coordinate grid before, because it's just always kind of been known in what I've taught. But remember, it's x, y is the order of points. So when you have a point, the first one's your x, the second one's your y. Okay, and that's alphabetical, right? So we can remember that. So this is the first number of the order pair is called the x-coordinate. The second number is called the y-coordinate. It identifies the position with regard to the y-axis. So the point 43, okay, the point 43 is shown on the grid below for P. It goes over 4, up 3. That's point 43 right there, okay? All right, any questions on that so far? Okay, so let's go ahead and just do these really quickly. So for example 1, let's fill out these. So what is A? Let's kind of go around. Chris, where's A at? 2, 4, good. Okay, where is B at, Taylor? Close. What's first? You went left first, right? You always go left first, so your -3 would be the first number. Okay, because there is no up and down movement, and that's very common. Okay, -3, 0. It went over -3 and stopped, so it didn't go up or down at all, so it's 0 for the y. Up and down is y, left and right is x. Okay, good. Josh, what do you got for C? 6, -3, good. Okay. Breezy, D. Right, 0. We didn't move left and right at all, so 0, down 3. Good. 0, -3. Very well done. And over to you, Allie, for O. Right, that's the origin, correct? Very good. Okay. In terms of quadrants, does anybody remember how quadrants are numbered? Counterclockwise, but where does it start? Top right. Well, how can you remember that? Why is that an important section? It's kind of a, yeah, it's positive, positive. That's the section where everything is positive. 3, 4, 5, 6, all this is positive, positive. This right here is your quadrant 1. They usually use Roman numerals, but you can just call it 1. This one's 2. I know you guys aren't very good at Roman numerals from that factoring practice. 3 and 4. So it goes counterclockwise. 1, 2, 3, and 4. So then that question now says, write the coordinates of the point in the second quadrant. So what point's in the second quadrant? E. So what is E? What is E, Tatum? 0, 3. Okay. Well, if I had 0, 3, it would be right here. So what'd you miss? What way we have to move? 2. Okay, what kind of 2? Because we're going left. Is left of negative or positive? -2, 3. Does that make sense? Yeah. Whoa. That was weird. Okay, so E is -2, 3. Left 2. Okay, and you should start kind of in your head. You should start thinking when you're making a left movement on a coordinate grid, you're making a negative movement. When you're doing a down movement, that's a negative association, right? So think left and down as negative movements, up and right as positive movements. Does that make sense? So when I move to the right, that's positive. When I move up, that's positive. When I move down, that's negative. When I move left, that's negative. Okay? All right. Write the coordinates of the point in quadrant 3. Okay, there's got a lot of stuff going on here. Let me erase all this real quick so we can see. Okay, what is in quadrant 3? Let's go to Alex. Yeah. F is good, and what is F? -4, -3. Good. Negative, negative. Okay, complete the following table using positive or negative. So in quadrant 1, the x coordinates are what? Positive or negative? Positive. The y coordinates, right here. Positive. Okay, quadrant 2, over here, my x coordinates are? And my y's? Good. Quadrant 3, negative and negative. Quadrant 4, positive, negative. Good. They're pretty good with that so far. Okay. All right, next page here. All right, so describing the pictorial pattern using a linear relationship. So 3 toothpicks used to form a triangle. A second triangle is formed by adding 2 more toothpicks. Third triangle is added by adding 2 more toothpicks, etc. Says draw the next 2 diagrams of the pattern. So from this picture, draw the next 2. So every time they're adding 2 toothpicks, so it would be, let's see here. That's where we're at now. So I'm going to add 2 more. So it's going to be 1, 2. That's the next one. And the next would be so that would be your next one. You're adding 2 because you're building off of sides already there. Triangles have 3 sides. So when you start it, you already have a side of your triangle that you're reusing. Okay. Complete the table relating the number of toothpicks P to the number of triangles T. So triangles, we have 2 triangles. So 2 triangles, how many toothpicks do we have? 1, 2, 3, 4, 5. Okay, at 3, 1, 2, 3, 4, 5, 6, 7. At 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. Bless you. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that goes up by 2 every time. Represent the data from the table of values on the grid. So we're going to plot these as points now. And this is where the Cartesian coordinate grid is like what we want to use for. Okay, is showing relationships in a linear form. Okay, so 1, 3. So we can use any scale we want. We don't have any huge numbers, so I'm just going to use our normal like 1, 2, etc. So 1, 3 would be right here. Oh, wait. Yep, toothpicks, I'm sorry. Okay. Okay. T for triangles. So this is essentially our X. This is essentially our Y. 2, 5. 1, 2, 3, 4, 5. Okay. And it's going to be there for 3, 7. It's going to be there for 4, 9. And it's going to be there for 5, 11. So there is our data like represented on a grid. Explain why it does not make sense to join the points in a straight line. So on this example, why does it not make sense to join them on a straight line? Alex?
Because, like, if you showed them, it shows, like, how many toothpicks you use, like, 1.5 triangles.
Exactly. Does that guys make sense? That's a very good example. So she's saying that if I connected these, this means that there's values here. Well, you can't have, like this is between 1 and 2. I can't have a point right here at 1.5 and then, what would that be, 3.5. So I'm saying at 1.5 triangles, I have 3.5 toothpicks. We can't do that, not according to our directions. Our directions are using whole toothpicks and whole triangles. Does that make sense? So in this case, for representing this data, we don't want to connect it. Good. Anything else on that part? Okay, so describe the relationship. So I'll just put can't have half triangles or toothpicks. I'll put TP for toothpicks. Okay. Describe in words the relationship between the number of toothpicks and the number of triangles. So what's the relationship? See if you can figure it out. It's a pattern. It's not just +2. So the triangles and the toothpicks have a relationship. So I want you to look at this number and how can you get to 3? This number, how can you get to 5? That same pattern. Got it, Molly? What is it? Right. Good. Multiply number of triangles by 2 and add 1. So 2 times 1 is 1 plus 2 is 3. 2 times 2 is 4 plus 1 is 5. 2 times 3 is 6 plus 1 is 7, etc. So times 2 plus 1. Now it says write that as an equation. So how can I write that as an equation? So that means that P for toothpicks is equal to 2T plus 1. 2 triangles plus 1. 2 triangles plus 1. Okay? G, use the equation to determine the number of toothpicks if there's 27 triangles. So there's 27 triangles. Where do I put the number 27? In for T. So I'm going to go P equals 2 times 27 plus 1. 2 times 27 is 54, plus 1 is 55. So that means there'd be 55 toothpicks for that example. And then it says also use the equation to determine the number of triangles if there is 83 toothpicks. So now where do I put the 83 at? For P, and so now what changes? What do I have to do now? It's not as straightforward because I have to do what? We have to solve. Exactly. This pen's working good down here. Okay, so I'm going to have to minus the 1, divide the 2. Does everybody see that? Minus the 1, divide the 2. So that gives me 82 equals 2T. Divide 2, I get 41 triangles for 83 toothpicks. Okay, awesome. You guys are doing good? All right, on the next example here. Okay, slow me down if you need anything. Okay, this is it's a very basic concept, but a very important one because, again, XY coordinates, we use those all the time. So again, I know I said this a billion times. I feel like everything in Math 10 builds to Math 20 because we use XY coordinates all the time. Okay, students in physics classroom determine the resistance in an electrical circuit by measuring the voltage, V volts, when the current, Li amps, I guess using I for amps, okay, was passed through a circuit. The table below shows the results. So here's the results. Okay, and then we have represent the data on the table of the grid. So it's important to understand which ones are dependent variable and are independent variable. So if I said X, when you plug in X, it gives out a Y, right? An input of X kicks out a Y. Do we understand that kind of concept? Because that makes X what? Independent. So Y is always dependent on what X is. Okay? So Y is always dependent on what X is. As X changes, Y changes. Okay, so now in this problem here, which one's the dependent one? So determine the resistance of the electrical circuit by measuring the voltage in volts when a current of amps was passed through the circuit. Okay, so does the amps affect the volts or the volts affect the amps? If amps affect the volts, good. So what that means is this is essentially my X, this is kind of my Y in terms of our mind. Okay, how we're thinking about it. So we're going to represent on the grid here. I think I went, see here, 1, 2, 3, 4, 5. I went by every 5 spaces with a 1. 1, 2, 3, 4, 5, 1. 1, 2, 3, 4, 5, 2. 1, 2, 3, 4, 5, 3. Man, this pen, I got to recalibrate after this. Oh, right in that spot. And 5. Okay. And then going up, I went by, every 5 was 10s. I went by 2s. So this is 10, 20, 30, 40, 50. Okay, so I'm going to plot them. So at 0.5, I'm at 6. So 0.5 would be 2, right there, right there. My first one. And at 1.5, I'm at 18. Right there. At 3, I'm at 36. Right there. 3.5, I'm at 42. Right there. And at 4, I'm at 48. Right there. So you can see we have a pretty good line here. Okay, we got a pretty good line there. Okay, it says, does it make sense to join the points together with a straight line? So in this case, can we have in between amp, like can we have 2 amps go through? Yeah, so this time it's okay to connect them. So yes, it makes sense. Because the data is continuous. Okay. Use the graph to determine the voltage for a current of 2.5 amps. So 2.5 amps would be here. I want to figure out what that's going to be. Looks like it's going to be 30 amps. Or excuse me, 30 volts. Excuse me, 30 volts. Comes from 2.5 amps. Okay. Write an equation representing V in terms of I. So how is it growing? How is it growing? So what you can do is look at your table. Is there any spots in your table that are 1 apart? And how much did it go up by? We always want to figure out the relationship in terms of for every 1, right? So like for example, look at 0.5 to 1.5. How much did it go up by? Okay, good. And then go over and look from 3 to 4. How much did it go up by? 12. Do you guys see that? So the relationship of the volts to the amps is 12. So volts is equivalent to 12I. So 1 volt would be 12I, 12 amps. Or I said it backwards. 1 amp would be 12 volts, excuse me. Okay, use the equation to determine the voltage when the current is 6.2. So now we don't have to worry, we don't have 6.2 in our graph. So what we're going to do is we're going to put 6.2 where? For I. So V equals 12 times 6.2. That's going to give you volts of 74.4. Okay, and then the last one, so the resistance is calculated from the equation V equals IR, so amps to the resistance. Take the resistance in the electrical circuit. So what's the resistance? Well, if we solve for R, what do we have to do? If V equals IR, and I want to solve for R, well, we know I happens every what? 12, right? So if I divided 12 off, that's the resistance, because that's what I'm dividing by. So your R would be 12. They call it ohms. Okay, we just got a little bit more, and I'll give you guys some time to practice. We'll take a break. All right, last page. All right, so discrete and continuous variables. In class example number 3, the variables I and V are examples of continuous variables since they can take on every value with a particular interval. Variables which is impossible to find intermediate values, and any two values for this graph example, it was okay, between 0 and 5. In example 2, the variables P and T cannot only take on limited values, okay, so example 2, so let's go, sorry, we just did example 3. Example 2, it was not continuous because it cannot take halves. We can't do half of triangles. Those are called discrete variables. So that means if you have restrictions on what you can have in terms of whole and not whole, that will create something that will be non-continuous, which is not going to be something you can connect lines with in your graph. Okay, so these are examples. Okay, so classify each of the following variables as discrete or continuous. Time taken to complete a 100-meter sprint. Is that continuous or discrete? Can I finish a 100-meter race in 10 seconds? Can I do it in 10.6 seconds? Yes, so then it's continuous. Okay, there's no limits on when I can finish the race. Number of students who pass Math 10. So unfortunately, as much as we'd like to, we can't cut Xander in half. We can't have 12.5 people pass. You either pass or you fail, right? So it's got, you can't have half a person. Okay, so this one would be discrete. Height of students. I mean, realistically, even if Chris and I are both 5'10", if we really got down to it, he might be 5'10.3", and I might be 5'10.2", right? We might not all be exactly 5'10", so that would be an example of continuous. You know there's infinite amount of heights, right? We talked about that in Math 9. No matter what, okay, I don't know if you've ever heard this before, but if you had a line here, whoops, can't right there. If we had a line here and a line here, let's say right here, I just made this, let's say it's 2 inches. Okay? There's an infinite amount of distance in that space. Okay, the reason being is, I can say I just cut a spot at 0.9. Then I can cut another spot at 0.99. And then another spot at 0.999. I could keep doing that for the rest of my life and not be done. Okay? There's an infinite amount of spaces or lengths that you possibly could have. So that's an example why it's continuous. There's no problems. You understand that? So with height, there's an infinite amount of heights we can have. Okay? Shoe size. So when you go to the store, shoes come in what? Halves and wholes, right? So that's discrete. There actually is limits. I don't know very many people. Has anybody got a 10 1/3 shoe before? No? Okay. So say if you have, I think that's my size. I really need that. Or no, mine's 11 1/3. Half's too big, 11's a little too small. Okay? All right. Go ahead.